One of the questions idiomatic to classical quantitative modeling asks, how fast is a system changing right now? The concept of right now corresponds to a single moment, but change is evaluated by comparing the system's conditions at distinct times separated by finite intervals. The concept of a limit will be useful in future modules when we need to relate concepts seemingly defined in terms of one instance in time with concepts intrinsically defined in terms of finite time intervals. The concept of a limit is a tool that allows us to analyze the behavior of a function. Using limits, we can describe how a function approaches a finite value, or, for example, how a function increases without bound. These behaviors can occur as x approaches a particular value, as well as when x increases without bound. Crossing these possibilities produces a 2x2 chart of 4 types of limiting behaviors. In the first video in this slide deck, we will describe the concept of the limit of a function approaching a finite height at a finite value of x. In the second video, we will define improper limits. In the third video, we will describe finite limits at infinity, and in the fourth video, we will describe infinite limits at infinity. It is important to understand that not all features of functions can be described by these cases. In the fifth video, we will emphasize that limits do not always exist. Finally, we will close in the sixth video with a worked example illustrating how the concept of the limit can be explicitly applied to analyze a simple linear function. In this video, we begin by defining the limit of a function as x approaches a particular value. For each definition in this slide deck, we will present notation, a short vernacular description, a symbolic definition, an expanded description in English, and an animation. We read this notation as the limit as x approaches a of f of x is L. This means that as x becomes arbitrarily close to a, f on x becomes arbitrarily close to L. This definition can be made more precise using mathematical symbols and, as an alternative, using an expanded English description. We first provide the definition using mathematical symbols. The upside-down A is read for all. The backwards E is pronounced there exists. The S.T. is short for such that, and the double-struck arrow is short for implies. Unpacked and converted into standard English, these symbols together mean, for all positive epsilon there exists a positive delta such that confining x to the two-part domain whose left half is between a minus delta and a, and whose right half is between a and a plus delta, implies that f on x is also confined to between epsilon above and below y equals L. In mathematical symbols and unpacked English, limit definitions can be dense. To provide a graphical understanding for this definition, we plot f on x versus x for a generic function. The golden circle marks the point with coordinates x equals a and y equals L. We begin to animate a process that illustrates what it means for L to be the limit as x approaches a of f of x. We shade the vertical interval between L plus epsilon and L minus epsilon. We can choose a positive delta to define a pair of intervals of x values, one between x equals a minus delta and a, and the other interval between x equals a and a plus delta. Can this be done so that within the domain consisting of these two blue intervals, the yellow curve is assured to remain vertically confined to the golden interval? The blue intervals we have just revealed, which exclude the dashed blue lines at precisely x equals a minus delta, x equals a and x equals a plus delta, are, together, an example to the affirmative. In the graphical convention we will use, a dashed line denotes exclusion from a shaded region, while a solid line denotes inclusion in a shaded region. For this narrower golden band corresponding to a smaller epsilon, we can still find a delta, which is now smaller, to define blue bands within which the yellow plot of f on x versus x remains vertically confined to the golden interval. Even after epsilon and thus the golden interval shrink again, we can still continue to identify yet another delta, with corresponding intervals of blue shading, within which the yellow plot of f on x versus x remains vertically confined within the golden interval. Consider the possibility that the process illustrated over the last couple of slides can be continued by investigating finite values of epsilon that become small without restriction. Consider the possibility that, no matter what epsilon we investigate, there always exists a suitable finite delta to specify blue bands within which the yellow curve is guaranteed to be vertically confined to the golden band. If these possibilities are satisfied, then L is, in fact, the limit as x approaches a of f of x. Now that we have defined the limit of a function, we check the viewer's understanding by asking, can L still be the limit as x approaches a of f of x if, as illustrated, f of a itself does not equal L? Please pause the video to consider this question. Yes, L can be the limit of f of x as x approaches a, even if f of a itself is not equal to L. Observe in the formal definition in unpacked English that the horizontal position x equals a is excluded from those two intervals of values of x between x equals a minus delta and a on the left and between a and a plus delta on the right, where we are horizontally confining x in our attempt to confine f of x vertically to a range between L plus epsilon and L minus epsilon. Thus, the value of the function exactly at x equals a is irrelevant to the limit of the function at x equals a, because the value of the function at x equals a appears nowhere in the definition of the limit. We have just presented the epsilon delta definition of the limit of a function. This definition is relevant when the plot of the function vertically approaches a particular finite height while horizontally approaching a particular value of x. Some functions have plots of f of x versus x that become arbitrarily large. These situations can be analyzed using the concept of an improper limit, which we define in the next video.